Howdy, howdy. This is Mr. Potter. Today we're going to be talking about rational functions. And to start talking about this, we actually want to first start talking about the idea of a limit. Because keep in mind, if I take a look at a function like 1 over x, one of our parent functions, let me go ahead and graph that over here. So I know the behavior of this function. I know that I'm supposed to have a graph that looks kind of like this in the first quadrant and something like this in the third quadrant. And I know that I have asymptotes. I know that I have a vertical asymptote here that my graph can't touch. And I also know that I have a horizontal asymptote here, which my graph gets closer and closer to. And so what happens is that I have some areas of behavior where the function's not defined, but the function gets closer and closer to a particular value. I happen to know over here that as x goes to negative infinity, f of x goes to 0. So I can write a sentence like this, or I can say that the limit as x approaches negative infinity of f of x is equal to 0. And a lot of mathematicians will use this notation to talk about the behavior of the function as x approaches a particular value. So similarly, I could say the limit as x approaches infinity of f of x is equal to 0 as well. Because as x gets bigger and bigger and bigger, my graph is getting closer and closer and closer to a y value of 0. So I can use this notation when I'm talking about approaching a particular asymptote, a horizontal asymptote, but I can also use this notation when I'm talking about these vertical asymptotes. I can talk about what happens as x gets closer and closer to 0 from the negative side. So as x gets to 0 from the negative side, f of x decreases without bound. And of course, this is just fancy talk for talking about heading towards negative infinity. So I could write this for the limit as x approaches 0 from the left, and I'm using a minus to show that it's approaching from the negative side of 0, of my function equals negative infinity. And similarly, I can talk about this behavior over here by saying that the limit as x approaches 0 from the positive side, from the plus side of infinity, of f of x equals positive infinity. So I can use this to talk about the behavior of these rational functions, these functions that have horizontal and vertical asymptotes, because I can talk about the property, about what's happening as I get closer and closer to these places where my function is undefined. My function's certainly not going to be defined at negative infinity or at positive infinity, and because of division by 0, my function's not going to be it's not going to be defined for values of x at 0. But I can talk about the behavior of the function. I can talk about the graph of the function. And these are what are happening in the tables. If I'm looking at a table of x and f of x, I can talk about looking at what's happening at point 1 or 0.01 or 0.001 or 0.0001. These values are 10, 100, 1,000, and 10,000 respectively. And I notice that as I get closer and closer to 0, these values are increasing without bound. They're getting closer and closer to infinity. But of course, this is not actually a value on my table because it's not a value on my graph. X equals 0 is not in the domain. But we can use this idea of a limit to talk about what the behavior should be as x approaches these troublesome values. So let's do another example of this. Let's talk about this graph here, 1 over parentheses x minus 2 plus 3. Now, just looking at this, I'm looking at this as a translation. So I'm translating up 3 units and right 2 units. And we talked about what happens when we transfer a graph. Adding to the value increases it, and inside the parentheses with x, that's the opposite behavior. So a minus is to the right, a plus is to the left, which means that normally my graph would be centered at 0, 0, but my graph is being translated up 3 units, which means this asymptote that I used to have at y equals 0 is now a horizontal asymptote at y equals 3. Similarly, my vertical asymptote, which would be through the origin, is going to be a vertical asymptote over here. And so my graph ends up being translated up and to the right. But I can still talk about what's happening in the context of limits. I can talk about the limit as x approaches infinity of my function g of x. As x gets bigger and bigger and bigger, my graph gets closer and closer and closer and closer to this line at 3. And so the limit as x approaches infinity of g of x is 3. Similarly, as x approaches negative infinity, g of x is getting closer and closer and closer and closer to this asymptote. It's getting closer and closer to a y value of 3 as well. But of course, what's more interesting is what's happening at this vertical asymptote. Because x equals 2 isn't in my domain, I can talk about what happens as I approach 2 from the left, and I can talk about what happens as I approach 2 from the right. As I approach 2 from the left using values that are less than 2, so 1.9, 1.99, 1.999, this is decreasing without bound. It's heading towards negative infinity. Similarly, as I use values like 2.1, 2.01, 2.001, as I get closer and closer to 2, this is getting bigger and bigger. So we have this notion of what's happening with our graph as x approaches these troublesome points, and we can express those with limits. So something slightly more complicated, let's take a look at this function here. So I got f of x equals 3x plus 9 over x plus 4. And of course, this looks a little bit more troublesome because I don't have f of x being equal to 1 over x minus something plus something. It would be really nice if I had something like this. Luckily, we have the ability to divide this into this. If I do that, I'm going to have negative 4 going into 3 and 9. Synthetic division, just to do something really quick. So I drop the 3. 3 times negative 4 is negative 12, which gives me a negative 3. So what I've really got here is I've got f of x is equal to 3 plus a negative 3 over x plus 4. And so I'm looking at this and I'm seeing that I'm going to be translating up 3 and left 4. So my graph is translated as such. And of course that negative 3 that's on top of the fraction, that's just a dilation. That's going to make my graph stretch vertically. But it's also going to change the sign of things. So my asymptote's been shifted to the left 4. Here's my my vertical asymptote. My horizontal asymptote is still at 3 like the previous problem. But because of this negative, instead of being in quadrants 1 and 3, my answer is going to be in quadrants 2 and 4. So when I'm talking about my limits, if I talk about the limit as x approaches negative 4 from the left, as I approach negative 4 from the left, I'm going up. And so my function has a limit that's actually a positive infinity, even though it's approaching from the left. Similarly, as x approaches 4 from the right, f of x is actually coming down this way as x approaches negative 4 from the right, negative 4. So I'm getting closer and closer to negative infinity. So it's interesting to talk about what's happening here. And then we also need to make sure that we understand what exactly our domain restrictions are. Keep in mind that we want to know when is our denominator equal to 0. And that's, of course, happening at x equals negative 4. So this is a bad point. So my domain is all reals except x equals negative 4. So in other words, my domain is going to be from negative infinity to negative 4, along with from negative 4 to positive infinity. So from negative infinity to negative 4, and from -4 to positive infinity. Basically everything except for this point. Because dividing by 0 is bad. That's always going to be one of the things that restricts our domain. But keep in mind that I could have a situation where even though it's not in my domain, I don't have a horizontal asymptote. That's a very special situation, which we call a removable discontinuity. So I'm going to have a slightly different function up here. I'm going to change my function slightly. I'm going to rewrite it as 3x minus 9 over x squared minus 9. And I want to talk about this from purely an algebraic standpoint. From purely an algebraic standpoint, I can factor this numerator because I can factor a 3 out, and that's going to leave me with the term x minus 3. Similarly, I can factor the denominator and get x minus 3 and x plus 3. And I notice that I have a common factor in my numerator and my denominator, that x minus 3 term. So if I was to eliminate that term, my function would actually be equal to 3 over x plus 3. Now again, this is with the proviso that x is not equal to 3, because x equals 3 is not in the domain of my original function. It causes my denominator to be 0, but it doesn't cause this to be 0, which means if we have a common factor in the numerator and denominator, that can be eliminated in the denominator, then our graph and our function has a removable discontinuity. And I'm just going to call it RD because this is a lot of work. So when I'm looking at my graph here should look a lot like this graph. And of course, looking at this graph does not have anything being added. I don't have a vertical shift, but I do have a horizontal shift. So my graph should look something like this. So at x equals -3, I should have a vertical asymptote. And of course, I've got a horizontal asymptote here at 0. But I also know, because this is a factor of my denominator in my original problem, I know that something special happens at 3. Now, normally what my graph would look like is I'd have something like this and something like this. But what really happens is I actually have a hole right here. Right here at 3, there's a hole. And I get really, really close to 3. 2.9 is perfectly acceptable. 3.1 is perfectly acceptable to substitute into this, but I can't plug a 3 in here. But I could plug a 3 in here. So I could talk about the limit as x approaches 3 from the left, or I could talk about the limit as x approaches 3 from the right of my function. Let me call this f of x. So what I'm looking at here is, because I could divide that out, I could try substituting a 3 in here, and 3 over 3 plus 3 is 1/2. And if I do the same thing over here, I'm also going to get 1/2. In other words, as I get closer and closer to 3, my hole is precisely at the y value of 1/2. It's a removable discontinuity because I could define another function. I could say that g of x is equal to a piecewise function, where it's equal to f of x, where if x is not equal to 3 or x equals not equal to -3, but I could say that it's equal to 1/2 when x equals 3, and my graph would in fact fill the hole. It would say, hey, for this point, just go ahead and define a point right there. Everything else is going to be exactly the same as before. I'm still going to be undefined. But we call this a removable discontinuity because I could remove the discontinuity. I could fill the hole if I defined a function piecewise. to cover it up. So removable discontinuities are another thing that can happen whenever we have division by 0. It doesn't always have to be a horizontal, or excuse me, a vertical asymptote, but of course it always often is. So let's continue with this. So where do horizontal asymptotes occur? Horizontal asymptotes occur when the degree of the numerator is equal to or less than the degree of the denominator. And of course, we really have two cases here. If they're equal to, then y equals y equals some constant is going to be my horizontal asymptote. If it's less than, then y equals 0 is going to be my horizontal asymptote. The idea here is, of course, that if I have the degrees being the same, then when I do long division, I'm going to have some constant that's going to be my quotient, some nice number that's going to be up here. So let's do an example of that. Let's say I've got y equals f of x, which I'm going to define as 2x squared minus 4x plus 7 over x squared minus 5x plus 6. So again, this is a nice factor here. If I take a look at this denominator actually factors rather nicely to x minus 2 and x minus 3. My numerator actually does some factoring as well, I believe. If I look at that, 2 times 7 is 14. No, that's not going to factor nicely. Never mind. This is an ugly denominator. But if I do the division, if I go ahead and divide this out, x squared minus 5x plus 6, and I divide this into 2x squared minus 4x plus 7, I know it's going to go in 2 times, because 2 times x squared gives me the 2x squared. If this denominator had a degree that was bigger than the numerator, then all I'm going to have is just the remainder part. It's not going to work out nicely. But if the degrees are the same, then I'm going to get a number here. In this case, my number is 2. 2x squared minus 10x plus 12. Change all of my signs. That's going to leave me with 6x minus 5. And so now what I've got is I've got 2 plus 6x minus 5 over x squared minus 5x plus 6. And because the denominator factors, but neither of these factors are equal to my numerator, I know that I'm going to have vertical asymptotes at x equals 2 and at x equals 3. I've got a horizontal asymptote at y equals 2, and this allows me to get my sketch on. So if I take a look at this, I know that something's going to happen at x equals 2. Ooh, horrible line. I know something's going to happen at x equals 2. I know something's going to happen at x equals 3. And I know that these are going to be asymptotes. And I know that I have a horizontal asymptote at y equals 2. And so I have my graph. Now, when I'm doing this, if I want to graph this, I actually want to try values of x between the asymptotes. So in other words, I want to try something from negative infinity to 2, something from 2 to 3, and something from 3 to infinity. So if I try these out, let's see what happens. So if I have x equals 0 and substitute it into my original function, that's nothing, nothing 7 over nothing, nothing 6. So that's going to give me the point 0 and 7, 6. 0 and 7, 6, that's just right about here. And so that means that because I've got an asymptote and an asymptote, I'm going to have to be bound by those asymptotes. Similarly, if I try something bigger here, like say 10, it's going to be 200 minus 40 is 60, 167 over, this is going to be 100 minus 50 is 50 plus 6, 56. It's positive. Really, that's what I'm interested in. This is like 3 point something, so I'm going to be up here-ish. So I'm going to have something like this. The question then, of course, is what happens in between? So looking at this, if I take something at 2.5, that's going to be a little bit more of a challenge. But what I actually find is that my graph does something like this. I cannot cross these vertical asymptotes. That's something that I'm going to have to watch out for. I can never cross a vertical asymptote. The horizontal asymptotes, on the other hand, they're really more of a suggestion. Obviously, they're hard at negative infinity and positive infinity for rational functions. But I can into a situation where I do have something happening in between my vertical asymptotes. And we're going to do an example of that in a little bit. But we do also have something called a slant asymptote. That looks awfully familiar. So when I'm dealing with a slant asymptote, this is where the degree of the numerator is exactly one more than the degree of the denominator. So, in other words, I'm going to have something where my degree is just one more than that. So let's say I've got y equals g of x as 2x squared plus 6x plus 5 over x plus 3. Notice here that Notice that my denominator has a degree of 1, my numerator has a degree of 2. So my numerator is 1 more than my denominator. If we do long division, or if we do synthetic division, here's I'm going to have the 2, the 6, and the 5. Drop the 2. 2 times negative 3 is negative 6. That's nothing. Negative 3 times 0 gives me a remainder of 5. So this is really equal to 2x plus 5 over x plus 3. Notice that this looks a lot like what we were doing before, except this is actually a function. It's not just a constant. So instead of having a horizontal asymptote at 2, like we would be led to believe, I actually have a slant asymptote. So what happens is normally my graph would have a vertical asymptote at negative 3. Again, because I'm not allowed to divide by 0. But I actually have a slanted asymptote that's going to be a line y equals 2x. And I'm not going to be able to cross this white line. So I've got a vertical asymptote here, and I probably should go ahead and extend this a bit. But I also have this slanted asymptote, or this oblique asymptote here. And so instead of being in one of the 4 quadrants, I've got to be in one of these 4 pizza-shaped slices. Of course, really nice pizza slice here. So if I take a look at this and substitute some values, if I substitute in, say, a negative 4, if I do g of negative 4, I'm going to find out that I have negative 4 times 2 is negative 8, plus this is going to be 5 over negative 4 plus 3, negative 1. So negative 8 plus 5 is negative 3. So I'm going to be, right, negative 8 and 5 over 1. So negative 8 and 5 is negative 3. So at negative 4, I'm going to be 1, 2, 3. I'm going to be here. Again, I'm subject to these walls, so I need to make sure that my graph stays in those boundaries. If I were to do something like g of 1, well, that's going to be 1 plus 5 over 1 plus 3, 4. So 1 plus 5 fourths, that's going to be, that's 1.25. That's 2.25. So over 1 up to 0.25. So I've got to be up here. And so this is what my graph ends up looking like. Of course, keep in mind that this is 2x squared plus 6x plus 5. This is all positive, so that's good. I'm getting this graph all above the line as it should be. So I want to do one more example here because I want to talk about how roots of rational functions can also affect, because keep in mind that if the numerator is 0, then my function is going to be equal to 0. Or undefined, again, if there's a common factor. But we're mostly interested in what happens when my function is 0, because these are going to be roots or solutions. So if I take a look at this, let's say I've got this function where I've got h of x is equal to x cubed minus 2x squared plus 24x divided by x squared plus x minus 2. If I take a look at this function, of course, I've got some nice factoring going on here. My denominator is going to factor to x plus 2 and x minus 1. My numerator, I can factor out an x out, and that's going to leave me with x squared minus 2x plus 24. So that's going to be x minus 6 and x plus 4. So I got roots, I've got solutions at x equals 0, x equals 6, x equals 4. I've got horizontal asymptotes at x equals negative 2, that should be a negative 4, and x equals 1. And I'm going to have a slant asymptote or an oblique asymptote because the degree of my numerator is bigger than the degree of my denominator. I'm going to have to compensate for all of this stuff. So let's do the division. So x squared plus x minus 2 going into x cubed minus 2x squared plus 24x. So I've got an x squared. Really, there's a constant term here I need to make sure I take care of. So x squared times x would give me x cubed plus x squared minus 2x, and change all of my signs. That's going to leave me with nothing. That's going to leave me with negative 3x squared. That's going to leave me with 26x. That's going to leave me with naught. And then I've got a minus 3, because negative 3 times x squared would give me negative 3x squared, minus 3x plus 6. And that's going to be 0. This is going to be 23x plus 6. So this function is really equal to x minus 3 plus 23x plus 6 over x squared plus x minus 2. So I have a slant asymptote that's at y equals x minus 3. So looking at the graph, here's what my graph has to look like. Okay, I'm going to draw it big, I'm going to draw it wide, make sure I've got everything covered. Y equals negative x minus 3. So here, 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 this is my slant asymptote. And it's going to extend down for a while. X equals negative 4. I've got a vertical asymptote here. X equals, excuse me, not there. That's not a slant asymptote. Why am I doing that? That's a solution. I actually crossed the axis here. Oops. Let's bring some of those back. Thank you. And at x equals 0 and at x equals 6, those are solutions. I've got a vertical asymptote at x equals 1 and at x equals negative 2. So my graph is subject to all of these boundary lines. So here my graph's going to have to do something like this, where it's going to be cut off by this vertical asymptote and by this slant asymptote, which goes off the bottom of the screen. Here, I've got a graph point right there. And then here I've got a graph point here, so this is going to be cut off by the slant asymptotes down here. I need to understand my behavior about what's going on right here. So I'm curious, what happens at negative 1? So if I take a look at what happens at negative 1, so I'm going to have negative 1 minus 3, so that's negative 4, plus, this is negative 1, so this is negative 23 plus 6, that's negative 17 over 1 minus 1 minus 2, that's negative 3. So I've got negative 4 plus, goodness, that's almost 6, so that's going to be up at 2. So I actually have something that looks kind of like this. And this is one of these weird, quirky things. If you take a look at this as Desmos or some other website, you're actually going to see that in between these vertical asymptotes, it's perfectly all right to intersect our y-intercept, or our slant asymptote. It's perfectly all right to do so. It's just when I'm dealing with these boundary cases that I need to keep those asymptotes immobile. Remember that I can never cross a vertical asymptote, but a horizontal or slant asymptote is really more of a trend line than it is a hard boundary that we have to watch out for, a hard boundary that we can't cross. Once again, this is Mr. Potter. Thank you for watching. Have a great day.